Hello, I'm Amit Langote. I work at Microsoft in its Postgres open source team. In this talk, I'm going to talk to you about how Postgres Executor interacts with modern CPU and how that impacts its OLAP query performance. I'll talk about a few things we've done to improve that, and then some architectural directions we could take in the future. So if you're interested in OLAP performance, please join me. Okay, so let's get started. So the title of my talk is Hacking Postgres Executor for Performance. So again, I'm Amit Langote. So I've been working on Postgres internals for over a decade at this point. In terms of how I started my community work with table partitioning that came in version 10. And I've been working on improving that over the many releases, along with many others in the community. I'm now at Microsoft, and I've previously worked at EDB and NTT OSS Center in Tokyo. I'm from India, but I've been living in Japan, Tokyo, for over 12 years at this point. Okay, so here's the agenda. So we'll start by grounding the talk. Why focus on executor performance? What kinds of overheads actually matter, and how do they show up in real-world queries? I'll talk about both OLTP and OLAP, but mainly OLAP. And then we'll look at how modern CPUs execute code, things like how they use caching and pipelining and branch prediction, followed by how Postgres Executor executes queries using the Volcano model, and why that model struggles when it comes to making good use of the CPU. Next, we'll cover improvements that are already committed, uh, things like reducing function call overhead, improving tuple deformation, and making scans more efficient. Then we'll look at the changes that go beyond these local changes, things like adding batching to the executor, push-based execution instead of pull-based execution, etc. And yeah, if you have any questions, you can ask them on Discord. And if you have something more you want to ask, you can just shoot me an email. Okay, so like in transactional systems, queries are short and often they just return a very few rows. In this case, executor startup costs like initializing plan nodes and tuple slots can dominate the total time. This shows up especially using prepared statements or extended query protocol, where you don't plan on every execution, but you have to initialize the plan, or you have to do the executor startup every time. On the other hand, analytical queries, they process millions of tuples, not just few. And each tuple has to go through the executors, things like doing tuple deforming, expression evaluation, and plan node dispatch, etc. And if that machinery doing all those things is not efficient, then these overheads can add up pretty quickly. And if you reduce those overheads, they can also show up significantly. So to summarize, OLTP, we care about improving the executor startup performance. And for OLAP, working on per-tuple throughput can make a whole lot of difference. And we can talk about both, but in this particular talk, I want to focus on things that help the OLAP situation. Okay, so let's start with some theory. First, on how modern CPUs actually work at the low level, and then we'll look at how Postgres execution model fits into that picture. Okay, so modern CPUs, they rely on multi-level cache hierarchy, kind of to hide the memory latency. So we have L1 cache that's extremely fast. It takes about 1 nanosecond to load from L1 cache. L2 and L3 are slower, but they are still faster than the RAM, which takes on scale of hundreds of nanoseconds to do a load. And to stay fast, CPUs depends on cache hits. So when data is already in cache, execution can just proceed smoothly. But when it's not, CPU has to fetch data from like slower memory, whichever it may be. So if it's not in L1, it has to look into L2. If it's not there, then L3, and then right. All this takes time. The second point is sequential memory access is more cache friendly because CPU can load one cache line and can reuse it efficiently across nearby accesses. On the other hand, if you have scattered access, then CPUs will run into many cache misses, and that can affect how it works on the program. So here I'm showing how if your program is accessing memory sequentially, it can just CPU can just fetch data into its L1 cache, and if you access, for example, an array, if you access it sequentially, then there's a guarantee that subsequent accesses will be served from the cache. On the other hand, if your program is accessing an array all over the place, then every access is going to run into a cache miss and result in a slow RAM access. So modern CPUs don't run one instruction at a time. They use pipelining, and what I mean by pipelining is that each instruction goes through stages, like you have fetch, decode, execute, and write back. So these are kind of roughly the four main stages. Of course, they are broken down into like smaller like micro stages, but I'm just going to mention these. So what this allows CPU to do is it lets it process multiple instructions at once. So one per stage and per cycle, as long as nothing stalls. But when an instruction can't proceed, like after a cache miss or a mispredicted branch, the pipeline has to stall. So in the diagrams that I'm showing here, in the left side, you have instructions just proceeding without getting blocked. But on the right hand side, I'm showing in cycle C3 when instruction I1 is executed, it runs into a cache miss. And what happens in the next couple of cycles is it has to wait for that cache miss to be resolved by fetching the data from RAM or whatever. And what happens is C4 and C5, nothing useful is really happening. I mean, I'm simplifying things here a bit. It's only that anything that depends on I1 has to kind of line up behind I1 getting unblocked. But in reality, CPUs can run anything that doesn't depend on I1 being finished. So, but I'm simplifying things here. If everything depends on I1, you are going to see a actual stall. All right. Another thing is modern CPUs don't wait to see how a branch resolves. It speculates. So CPUs will guess what path will be taken and begin executing instructions ahead of time. So what this does is it keeps the pipeline full and it avoids idle cycles. So if the guess is correct, all the speculative work gets committed as if the CPU had waited. So there's no time lost. But if the guess gets wrong, then the CPU has to backtrack. So it has to flush the pipeline. It has to discard the result of the speculative work that was done, and it has to restart from the correct branch path. That means that clearing the reorder buffer and refetching instructions, and it usually takes many tens of cycles. So branch mispredictions are one of the core causes of pipeline stalls. So when the CPU guesses wrong, it has to flush and restart, just like we saw earlier. So what are the main reasons for these? So one of the main reasons is data dependent branches. So here I'm showing a condition. So if the data of for stress threshold in this condition varies a lot, then the outcome becomes hard to predict for the CPU, and mispredictions will rise. So yeah, and the second reason is indirect branches. So things like if your program uses function pointers a lot, then the CPU has trouble predicting the target address. If there are if the program is using, there are direct jumps and indirect jumps. If direct jumps are hard to predict, sorry, easy to predict for the CPU, but anything that depends on a the jump address, if it has to be calculated, then CPU has trouble like predicting those target addresses. Okay, to summarize, all these techniques that we've covered, things like pipelining, speculation, caching, etc. All of those techniques rely on CPU seeing predictable control flow and memory access. If you have branch heavy code and unpredictable memory access patterns, then those things break that model, and the CPU spend time stalling and recovering instead of doing any actual work. If you're curious to go deeper into how CPUs actually behave, I recommend watching this talk by Matt Godbold. It's named "What Every Programmer Should Know About CPUs." I think it's a good overview and it's well worth watching. Okay, next, let's take a look at Postgres execution model. So Postgres uses the classic Volcano model. So the query plan is structured as a tree of operations. So scans at the bottom, joins, filters, and aggregations higher up, and execution flows top down. So if a node needs a tuple, it will call next on its child. So for example, here, aggregate will call next on join, and it will call next on its child two children, which are like base scans. And then the scans will actually read from the whatever table access or index access method that we have. So once a tuple is produced by the scans, it bubbles up back up the tree. So what's good about this model is it's very simple and it's modular. But as we'll see next, what it's not good at is using CPU efficiently. So in the Volcano model, each tuple triggers a cascade of function calls. So each node will call next on its children or child. So producing one tuple often means many function calls throughout the tree. What this does, it adds overhead, and it makes it hard for the CPU to predict control flow efficiently. And memory access is also scattered. So you have to move between nodes and buffers and tuple table slots, which hurts cache locality and it increases stalls. And each node typically has many condition checks, things like qual and projection and things like that, which adds more branches for the CPU to predict and, well, mispredict. And when these predictions go wrong, you get pipeline stalls and wasted cycles. Okay, so why can't compiler help optimize this code? Postgres query plans are built at runtime. What I mean by that is ahead of time compilation, meaning when you are building the package, you can't optimize for specific queries or plans. Of course, that's pretty obvious. So that raises the question, can we still benefit from compilation at all? In some localized parts of the executor, yes. So we've used inlining, for example, to specialize deforming logic and scan code paths, as we'll talk about in a minute, in a bit. But broader executor optimizations are much harder to optimize at compilation stage. So execution has to flow through function pointers like exec proc node, etc., which prevents inlining across plan nodes, and it hurts the many conditions will hurt branch prediction. The tuple access is also runtime dependent, so you have to check null flags and you have variable width attributes, etc., especially with row-based storage that we have in Postgres, which makes memory loads irregular and unpredictable. So that limits what the CPU can do with prefetching and, well, branch prediction, etc. We do have JIT, just-in-time compilation, but it only works for expression evaluation. And it does help reduce the interpretation overhead for expressions, but JIT doesn't restructure executor's control flow, plan node dispatch, etc. So JIT currently doesn't help the overall executor as such. So those the overall plan execution still remains dynamic. So to improve the executor performance at broader level, we'll have to look at some architectural rewrites that we'll take a look at towards the end. Okay, so now that we've seen how the executor interacts with CPU performance, let's now look at what's already been done to make things better. So in this section, we'll walk through some optimizations that we've committed over the releases, things like reducing function call overhead, improving cache locality, and reducing unnecessary branching, etc. And each one addresses very specific bottleneck in the execution model, but they were good improvements. Okay, so first let's look at expression evaluation. So Postgres used to evaluate expressions by walking the expression tree at runtime. Each node, like a constant or operator or a function, was processed via its own function call, which this meant that you would have deep call chains and many small functions, which hurts instruction cache locality, and it made it hard for the CPU to predict control flow. This was rewritten to use a flat opcode-based execution model. Instead of walking a tree, the executor runs a tight loop over opcodes, which is much better for the CPU. You have fewer branches and you have better cache usage, both data and instruction, and easier target prediction. With this change, expression evaluation in TPC-H, for example, was improved significantly, like by many tens of, like up to 30% improvement, even more in some cases. Next, reducing function exec proc node overhead. So originally, all plan nodes were executed by calling exec proc node, which looked at the node type and then dispatched to the right function for the plan node. This meant that you would have an extra function call for every tuple plus an indirect jump based on the node type, which hurts branch prediction and it adds overhead, of course. So now after this rewrite, each node stores a direct function pointer. For example, for sequential scan, its plan state node would store a function pointer of exec sequential scan, which is the execution function for a sequential scan. What this does, it avoids the centralized dispatch, and it also eliminates the per-tuple overhead of calling exec proc node in the first place. Yeah, and it also reduces CPU stalls because of branch mispredictions. Branch misprediction to predict the which node function, for example, would have to be called. And this also improved performance, even if it was a minor improvement, but coupled with some other improvements, this was a good improvement. Next, heap get page. So heap, we have heap access method. So this is not really executor code, but for sequential scans, improving heap fetch performance matters a lot. So before this change, every tuple fetched from heap page was checked for visibility and serializability. So even if those conditions didn't change for the whole page, the previous code would check these conditions for each tuple separately. So what this meant inside this loop on the page is that you have like repetitive branching, which CPU couldn't predict well. And the new approach, what we done here is the loop of reading tuples from page was kind of extracted into a new separate inlineable function called page collect tuples. And what it does, and it accepts these flags for check visibility and check serializability as flags. So the caller can just check if a page needs a visibility check or serializability check once for each page, and just pass the value of that flag to this function. And what the compiler does is it specializes that function based on the conditions, based on the value of these flags. So in each specialized variant of this function, you have fewer condition checks and fewer unpredictable branches. And this makes sequential scans run significantly faster, especially for all visible pages, especially if you do vacuum properly. Next, let's look at tuple deforming. These are the things we've done in version 18. Tuple deforming used to access information for each column by fetching the whole PG attribute struct, which is about 104 bytes per attribute. What that meant is you have to touch many cache lines for every column, which is especially bad for like wide tables with many columns. So this was replaced with compact attribute struct, which is a much smaller struct, which it kind of compresses the necessary information down to just 16 bytes. Those 16 bytes contain all the information that's needed for actual deforming. So now the deforming logic has to load fewer cache lines, and which improves cache locality and also reduces stalls due to mispredictions. Next, in tuple deforming, so previously we used to use this function called at align nominal for each column to compute alignment for loading that column's value into memory. So this involved checking type alignment, whether it should be 4-byte or 8-byte, etc. And it involved conditional logic. So these branches were hard to predict, especially for wide tables with mixed types, which led to frequent branch mispredictions in tight loops. Now we store required alignment value in the compact attribute struct that I mentioned in the previous slide. And it uses this micro type align, which has no branching, which is just a mask and add operation. This results in a branchless, faster deforming loop, which combined with having a smaller compact attribute struct improved performance significantly. And finally, in tuple deforming, there was one loop that handled all the cases. So you would have one loop would check for each column, would do a null check, variable length check, and alignment logic check. So there was no specialization. Each loop would check all these conditions for every column. Now we have a fast path that calls the inline helper function with pre-computed values for whether to check for nulls or not. So if you have this information in the tuple header, so you check if the tuple has nulls. If not, then it would just pass false for has nulls. And this function slot deform heap tuple internal will be specialized by the compiler because it's inline. Compiler can specialize it for different values of these, whether to use slow path or whether to check for nulls, etc. And so typically you would go through like fast path for the first few columns, for example. And once you hit like a null for the first time or a variable length attribute for the first time, then you enter the slow path. So if you have tables where you optimize type ordering, the new code can use fast paths. You can separate between fast path behavior and slow path behavior, which improves performance significantly. So together, these tuple deforming changes makes tuple deforming more CPU efficient because as we saw, we have reduced cache misses because we use smaller struct to store tuple deforming info. And also by reducing conditional logic, we reduce branch mispredictions. my colleague David Rowley did some many benchmarks, and he observed improvements of up to 25% in best case. And yeah, the improvement was pretty significant. Okay, finally, we also refactored exec scan to use inlining. So previously, exec scan handled all scan logic, so it would have check for check-in is evolve plan qual, the thing that's used for read committed isolation level is necessary, and whether we have quals or projections, etc. All of these things were checked like in one function, one general purpose function, and it was all these things would be checked for every tuple that would go through that function. So even when these features are not used, we would pay the cost of checking them for each tuple. Of course, that leads to mispredicted branches and yeah, instruction cache load because you have this big function. So the fix was to refactor the core logic into exec scan extended, um, which takes flags for EPQ, qual, and projection. And because these conditions are known during plan initialization, based on looking at the plan node, we can the compiler can look at these condition values, and it can specialize away the condition checks by generating fast branchless code for each like set of conditions. So for example, for sequential scan, you'd have like these different combinations and these different variants that are passed different values for these different features that need to be checked. So by inlining scan logic and eliminating unnecessary per-tuple branching, we make better use of CPU's instruction cache and reduce pipeline stalls. And yeah, I mean, these things add up. For a sequential scan, if you're scanning many millions of rows, these things add up. So the improvements, I benchmarked this, and in the best case, we saw up to 10% improvement of sequential scans, but on average, we could see up to like 5% improvement. Okay, so now let's look at where we can go next. So what kind of bigger architectural changes we can make to the executor. So things like adding batching, using push-based execution instead of pull-based, and using vectorization, things like that. Okay, so first, opcode-based or push-based execution. The traditional Volcano model walks the plan tree by calling exec proc node recursively. So each node pulls one tuple at a time from its child. So in an opcode-based model, we flatten this control flow into a pipe loop over compact operations. Each opcode represents an action, think like fetch from access method, filter, project, or whatever. And we execute these operations in sequence. What this does, it avoids recursive function calls and deep call stacks. It improves branch prediction, and it makes the instruction stream more cache-friendly. It also opens the door to more efficient JIT execution. For example, since the control flow is explicit and compact, it typically becomes like a one function instead of one function calling other function and so on. So this direction was outlined in 2018 by Andres Freund, my colleague, and much of what I also described in the previous slides kind of came from that thread. Okay, batch processing and vectorized execution. So in the current Volcano model, every tuple requires a call to next, which means that a function call for every tuple, plus any branching and dispatch that comes with that. So what batching does, it amortizes that cost by processing many tuples per call. Typically, some power up to, like you might process 64 or 128 or even more tuples per call. What this does, it reduces the number of function calls and improves CPU utilizations for reasons we discussed. It also, creates a more predictable execution flow, and yeah, of course, reduces branch predictions, etc. And if the storage is columnar or has a SIMD, single instruction multiple data friendly layout, batching also enables vectorized operations, so operating on entire column or like tuple groups at once. So this model fits better how the CPU wants to execute. What I mean by that is it wants full pipelines and fewer unpredictable jumps. Finally, compiled execution. So today we use JIT to speed up expression evaluation, but the rest of the executor still runs as a dispatcher. In a fully JIT compiled executor path, we generate optimized machine code for the full query plan, not just these expression trees. So that means that there is no per-tuple calls to exec proc node or branching to find the right node logic, etc. So control flow gets flattened into like one function as such. So everything becomes one single white loop. All of this eliminates like function pointer dispatch and branch loose predictions. So you are basically removing interpretation from plan execution. So what it allows the CPU to do is it can see and optimize the whole instruction stream across the plan, not just parts, the expression parts. Of course, the trade-off is compile time. So this makes the most sense for long running queries where startup cost is amortized. Okay, so that's all I had. Thanks for watching.